Welcome to the Deep Dive. This is where we take complex topics and, well, make them clearer for you. Quickly.
We do the digging, you get the insights.
Exactly. And today, we're diving into something absolutely fundamental. It governs pretty much everything. Force.
A core concept in physics, but really it's about understanding everyday life.
We've pulled together some really solid educational materials on this, and our mission, yours and ours, is to get a real handle on what force actually is.
How it affects things, the different kinds.
How we measure it. All clear, all engaging, hopefully some aha moments along the way.
That's the plan. Think of it like peeling back the layers. Understanding force. It's not just for exams. It helps you see why things happen.
Okay, so first things first. Our sources start with the basics. Rest and motion. Seems simple enough, right? Still or moving.
It does seem simple. The definitions are pretty straightforward, too. State of rest means no change in position compared to surroundings, like that book on your table, it's just sitting there. And state of motion, that's when it is changing position relative to its surroundings. A car driving past, maybe?
But, okay, here's where it gets a bit twisty. The material brings up sitting on a moving bus. Suddenly, it's not so clear-cut.
Exactly. That's a great example because it shows rest and motion are relative, depends on your viewpoint.
How so?
Well, on the bus, the person next to you, they seem perfectly still, right? You're both at rest, relative to the bus itself.
Okay.
But someone standing on the pavement watching you go by, they see both of you definitely in motion. So who's right?
Both, depending on where you're looking from.
Precisely. It's all about the observer and the surroundings, the frame of reference. It really makes you think, doesn't it, how we perceive things?
It really does. So if something is at rest and starts moving, or it's moving and it stops, something has to cause that change.
Yes. And that something, according to our sources, is force. It's the physical cause needed to alter that state of rest or motion.
And the simplest way to think about it, a push or a pull.
That's the core idea. Think about opening a door. You push it or you pull it. Simple actions, but they involve force.
Or drawing water from a well. That's a pull.
Kicking a football, a push. Moving furniture definitely involves pushes and pulls.
And this is important. The material notes that even if you push something really hard, like a huge wardrobe, and it doesn't move.
You're still applying a force.
Right. It's the attempt or the tendency to cause change that counts, even if it doesn't immediately work.
That's a really key distinction, the potential for change. So let's break down push and pull a bit more.
Okay.
A push is defined as a force causing motion away from the person or thing applying it, like pushing a door shut, pressing a switch.
A bulldozer moving rubble.
Pushing a baby stroller.
Or helping push a stalled car. All moving things away.
And pull, that's the opposite, bringing something closer.
Exactly. Pulling a drawer open, a gardener pulling a heavy roller.
A horse pulling a cart, someone pulling luggage on a trolley.
Even a rickshaw puller. The motion is towards the source of the force. And here's another fundamental point raised. Force isn't a solo act.
No, it always involves an interaction. At least two objects have to be involved for a force to even exist. You push on something, something pulls on you. It's an interaction.
Makes sense. You can't push thin air, really. Well, not effectively.
Right. Now, beyond push and pull, the sources introduce stretch and squeeze as types of force application.
Yeah, these aren't always the first things you think of.
But they fit. Stretch is when a force increases an object's length in the direction you're pulling. Think stretching a rubber band.
Or like a spring balance, when you hang a weight on it, it stretches out.
Exactly. And squeeze is the opposite. A force decreases length or changes dimensions, like squeezing a toothpaste tube.
Or squishing modeling clay.
So push, pull, stretch, squeeze. These are all ways force manifests.
Which leads us to a more complete sort of overarching definition.
Yes, the materials pull it all together nicely. Force is a cause, be it a push, pull, stretch, or squeeze that changes, or tends to change, an object's state.
What state?
Its state of rest, or its uniform motion, or its direction, or even its shape or size. It covers all the bases.
That's pretty comprehensive. And they give 5 key effects to make it concrete.
Right, let's list them. First, changing shape or size. We mentioned clay, balloons.
Squeezing dough, denting a bag of flour.
Second, making something stationary move, the classic kick of a football, or getting that stalled car rolling.
Third, changing the speed of something already moving.
Pushing a swing to make it go faster, or applying a little drag to slow it down.
Fourth, changing the direction of a moving object.
Like a cricketer hitting a ball changes direction instantly, or even waving smoke away.
They mention a cool little activity, too. Dropping cardboard and pushing it sideways as it falls changes its path.
And fifth, stopping a moving object altogether.
Catching a ball, putting the brakes on your bike.
But then comes that important question again. Does force always cause these changes?
Right, like if I push against this desk, I'm definitely applying force.
But the desk isn't, hopefully, moving or changing shape noticeably. So it reinforces that idea of tending to cause change. Other forces, like the desk's internal strength or friction, might resist your push successfully. The net effect might be zero change.
Okay, that clarifies things. So force has effects, but doesn't always succeed. Now the dive gets deeper into types of forces.
Yes, a very useful categorization. The main split is between contact forces and non-contact forces.
Contact forces. Sounds like they need touching.
Exactly. Direct physical contact is required. First up is muscular force.
The force from our muscles, or animal muscles, walking, lifting, pulling carts.
Then collision force, the force during an impact, like billiard balls hitting, short, sharp force.
And friction, or frictional force. That's a big one.
Huge. It's the force that opposes motion between surfaces that are touching. Try pushing a heavy sofa, you feel friction fighting you.
It's why things slow down, right? A bike coasting, a ball rolling, friction eventually stops them.
Correct. And then there's mechanical force. Force for machines using energy.
Like a car engine.
Perfect example. Or a train engine. Even wind pushing a sailboat, that's mechanical force from the wind acting on the machine, the boat.
The material also touches on friction being good and bad.
A real double-edged sword, yes. We need it to walk, to grip things.
But it also causes wear and tear, wastes energy as heat.
True, and we actually manipulate it. We increase friction with treads on tires or shoes.
Or grooves on grinding stones.
And we reduce it with oil, grease, ball bearings, wherever we want smooth movement.
Okay, so those are contact forces. What about the other kind?
Non-contact forces. Or force at a distance. These work without any touching. Seems a bit like magic sometimes.
Yeah, like magnets.
Exactly. Magnetic force is the prime example. A magnet pulling iron nails across a gap.
And it can push too, right? Repulsion.
Yes, like poles repel, unlike poles attract. The materials show diagrams for that. They even mention maglev trains using magnetic repulsion.
Cool. What else is non-contact?
Electrostatic force. Force from electrically charged objects.
Ah, the rubbing a balloon on your hair trick.
That's the one. The charged balloon attracts little paper bits without touching them. Static cling, basically.
Okay, magnetism, electrostatic. What's the third big one?
Gravitational force. Gravity. The ultimate non-contact force, maybe.
The force of attraction between anything with mass.
Anything.
You, me, the earth, the moon, tiny dust particles. It's universal, depends on the masses and how far apart they are.
So that's why things fall down. Apples from trees, rain.
Precisely. It's the Earth's gravitational pull. Water flows downhill because of it. Throw a ball up, it comes back down. Gravity.
And it's always attraction, never repulsion. The source makes that clear.
Always pulls things together. Which brings us to weight. Weight isn't the same as mass.
Right. Mass is the amount of stuff in kilograms, measured with a balance.
While weight is specifically the force of gravity pulling on that mass, measured in newtons, usually with a spring balance. It's a force.
So speaking of newtons, how do we measure force properly?
Good question. The standard international unit, the SI unit, is the newton, capital N, named after Sir Isaac Newton, of course. Of course. And what is 1 newton exactly?
It's defined quite technically. The force needed to make a 1 kilogram mass accelerate at 1 meter per second squared.
Okay, maybe a bit abstract.
It is a more intuitive feel. The force needed to hold up a small apple is roughly 1 newton.
Ah, okay, that helps. And there's an approximation given, too.
Yeah, 1 kilogram force, kgf, the force of gravity on 1 kilogram is roughly 10 newtons. Just a handy rule of thumb.
And since source has direction.
It's a vector. We often draw it as an arrow. Length shows the strength. The arrowhead shows the direction. A longer arrow means a bigger force.
Okay. And measuring it practically. Spring balances.
Spring balances, exactly. They rely on the fact that a spring stretches or compresses predictably when force is applied.
How does the common one work? The hanging kind?
The extension type. You hang an object on the hook. Gravity pulls the object down, stretching the spring inside. A pointer attached to the spring moves along a scale marked in units of force, maybe grams force or kilograms force, sometimes newtons directly. The more it stretches, the greater the force. Simple, but effective. Okay, nearly there. The material also covers action and reaction. Newton's third law.
Ah, yes. For every action, there is an equal and opposite reaction.
Sounds familiar. Examples.
Kick a football. Your foot applies force. Action. The ball applies an equal force back on your foot. Reaction. You feel it.
Or throwing a ball at a wall, it bounces back.
Exactly. The wall exerts a reaction force on the ball. They always come in pairs, equal strength, opposite directions. It's fundamental.
Okay, last main point. The net effect of force. What happens with multiple forces?
Right. Things rarely experience just one force. The overall effect of net force depends on all of them, their strengths and direction.
So if forces are in the same direction?
They add up. Two horses pulling a cart the same way, their forces combine for a stronger pull. The net force is larger, same direction.
Makes sense. And if they're in opposite directions?
Then they fight each other. The net force is the difference between them in the direction of the stronger one. Think tug of war.
Right. The stronger team wins, the net force is in their direction. And what if the opposing forces are exactly equal?
Like two people pulling equally hard on opposite ends of a rope.
Perfect. The net force is zero. They cancel out. No change in motion. The object stays put or keeps moving at a constant velocity if it was already moving. Balanced forces.
So to wrap this all up then, force. It's that push, pull, stretch, or squeeze.
The thing that changes or tries to change, motion, speed, direction, shape, or size.
We've seen contact forces like friction and muscular force needing direct touch.
And non-contact forces, gravity, magnetism, electrostatic acting at a distance.
And we measure it in newtons, often using a spring balance, remembering it has both magnitude and direction.
That's a pretty solid overview of the essentials from our source materials. It really connects a lot of dots about how the physical world works.
It really does. Which leads us to a final thought for you listening. We've seen how this seemingly simple idea, force, is woven into everything, from tiny interactions to planets moving. So consider this. What other everyday concepts, things we take for granted, might hide similar depths? What seemingly simple ideas could reveal a whole network of understanding if we just dove a little deeper?
Something to ponder.
Definitely. Keep looking for the forces around you. Thanks for diving deep with us today.